Welcome to this virtual CTC presentation about the construction of a destabilizing nonlinearity for discrete-time uncertain Lurye systems. My name is Balint Patartic, and I work in the Institute for Computer Science and Control in Hungary. I've been working on this topic with Peter Seiler from the University of Michigan, Joaquin Carrasco from the University of Manchester, and Balint Vanek. We acknowledge funding from the EU project FLIPACE. Before we go into the details, let's take a look at a motivating example. Suppose we have a flexible aircraft and we design a flutter controller, that is, a controller that mitigates the effect of the flexibility of the wings by using the aileron control surfaces. If the design is successful, then the resulting controller stabilizes the closed loop. However, saturation of the ailerons can impair the stability. Therefore, we also need to know if the loop remains stable, even with that nonlinearity included. Furthermore, the behavior of the aircraft is not entirely described by its nominal model. Hence, for a proper analysis, we need to take model uncertainty into account. To assess the stability of this loop, a method is required for stability analysis in the simultaneous presence of nonlinearity and uncertainty. In this presentation, an algorithm is provided for that purpose. Next, I'll describe the precise problem formulation. We first discuss the nominal case without uncertainty. The block diagram you see here is the discrete-time nominal Lurye system. It consists of the nominal system G that is a stable discrete-time SISO LTI system. G is in negative feedback interconnection with the nonlinearity phi. Phi is a nonlinear function slope restricted in the interval 0k. That means that between any two distinct points y1 and y2, the slope of phi is non-negative, and it is at most k. Let's take a look at some examples. Suppose this is the slope bound k. Then this is an example of a nonlinearity slope restricted in the interval 0k. This is another example. And this is one as well, because all of its sections adhere to the constraint. To analyze the stability of the Lurye system, we want to find the minimum of the slope bound k, such that the Lurye system has a limit cycle solution. This problem is difficult to address directly. Instead, methods to find the upper and lower bounds of this minimal k have been developed. Lower bounds are most notably provided by the absolute stability literature. We'll consider the upper bound calculation, hence the objective is to find the upper bound of the smallest k such that the Lurye system has a limit cycle. This problem is the subject of a previous paper of some of our co-authors. We'll review that solution first before extending the method to uncertain systems. This method can find the limit cycle with a fixed frequency. The condition for the existence of the limit cycle can be expressed graphically as follows. This is the frequency response of the nominal system at the frequency omega. The stability condition is articulated in terms of the phase of the system. Specifically, if the frequency response of the system is within the shaded domain, then it is guaranteed that there exists a slope-restricted nonlinearity in the interval 0-infinity, with which the system goes into a limit cycle. The angle of the boundary of this instability region depends on the chosen frequency omega. If we decrease k, the instability region shrinks. It is proven in the paper that decreasing k moves the boundary to the left. The minimal upper bound ku is found when the boundary passes through the frequency response of the system. Then, we know for sure that there is a slope-restricted nonlinearity in the interval 0ku with which the Lurye system goes into a limit cycle. Since this calculation yields ku only at a fixed frequency omega, it is repeated over a sufficiently dense grid. The frequencies in the grid are all rational fractions of pi. It is shown in the paper that this computation also provides the input and output sequence of G corresponding to the limit cycle. Hence, once we obtain Ku, we also get the input U and the output Y of G when the Lurye system is in the limit cycle. Using these, the exact nonlinearity is reconstructed with which the limit cycle is sustained. For this, we plot the negative u as a function of y. The negative sign of u is there because of the negative feedback in the Lurye system. These are the points we get as a result. For example, this pair of u and y end up at this point on the graph. A piecewise linear interpolation and constant extrapolation gives us the exact nonlinearity phi, which maps the output sequence of the limit cycle to the negative input sequence. Therefore, with this phi and with the right initial conditions, the Lurye system goes into the limit cycle depicted on the left. Using this method, we get saturations and piecewise linear nonlinearities that are usually interesting in practical applications. As shown in this particular example, we don't restrict our analysis to odd nonlinearities. The initial state of G required for the limit cycle is calculated with elementary methods. Next, the main result of our paper is elaborated. That is, the calculation of the slope bound and the reconstruction of phi presented thus far is extended to uncertain systems. Instead of the stable nominal system, we consider a robustly stable uncertain system. The uncertain system is the interconnection of two components. M, which is a stable discrete-time LTI system with two inputs and two outputs, and the uncertainty block delta, that is a stable discrete-time SISO system with h-infinity norm bounded by 1. This uncertainty block represents unmodeled behavior of the system, such as the response to high-frequency vibrations or dynamics neglected by model reduction. The objective is to find delta U and the minimum of Ku such that the uncertain Lurye system has a limit cycle. To derive the result, let me go back to the graphical stability condition used to obtain the slope bound for the nominal system. When the system is uncertain, the frequency response extends from a single point to a domain on the complex plane. It is proven in the paper that the frequency response of the uncertain system for all allowable values of the uncertainty is a disk such as this one. The response of the nominal system is not necessarily in the center. This allows the instability region to shrink even further. The minimal slope Ku is obtained when the boundary of the instability region is tangent to the disk. This fact lets us also compute the frequency response of the worst-case uncertainty delta U. The LTI uncertainty sample is then obtained by a standard interpolation technique explained in the paper. When we substitute this delta U into the system, the interpolation that results in phi is identical to the nominal case explained earlier. Note that the most prominent alternative method in the literature, the robust describing function approach, can only find an approximation of the uncertainty. With the solution presented here, we get both the exact nonlinearity phi with minimal slope bound Ku and the worst case uncertainty sample delta U. Let me illustrate this method by a numerical example. Consider this Lurye system with a stable second-order nominal system. So far, the example is taken from the paper describing the results for the nominal case. 15% model uncertainty is added to the system across all frequencies, which results in the uncertain Lurye system we'll analyze. First, we'll use the graphical stability condition. This is the Nyquist diagram of the nominal system for non-negative frequencies. We sample this frequency response over a grid of frequencies that are rational fractions of pi. Due to the uncertainty, the response of the system expands to circles at each frequency like this. Let us take a closer look at this area, because this is where the critical frequencies are. We perform the upper bound calculation for each of the frequencies on the grid, and search for the smallest Ku. For the nominal system, the frequency where the minimum occurs is 2/7 pi, and for the uncertain system, it is 2/9 pi. Let me get rid of the rest of the points for clarity. For the nominal system, we get the upper bound Ku equals 13.03. Because of the addition of uncertainty, the slope bound shrinks to 6.96. This is considerably less than what we got for the nominal case, especially considering that only 15% uncertainty was introduced into the system. This demonstrates that even a small amount of uncertainty can cause a significant change in the behavior of nonlinear systems. Consequently, we see that vital insight may be gained by the inclusion of uncertainty in the analysis of nonlinear systems. Let's see the nonlinearities we get for our example. This is the slope bound we obtained for the nominal system, and this is the reconstructed nonlinearity with which the nominal system goes into the limit cycle. The slope bound is smaller for the uncertain system. Therefore, we get an uncertainty that is less steep. This shows again that if uncertainty is present in the system, a less severe nonlinearity is sufficient for the existence of a limit cycle. Let's simulate the uncertain Lurye system in the time domain to further illustrate the results. For this, we use the nonlinearity obtained in the uncertain case. When we run the simulation with the nominal system, we see that the output oscillates but ultimately settles to 0. These are the results of the same simulation with 50 random samples of the uncertainty. Some of these samples show more oscillation than the nominal, nevertheless, they also all settle. If we use the worst-case uncertainty sample in combination with the right initial state, then we get the limit cycle predicted by our calculations. The initial conditions for the other simulations are comparable to this one. See the paper for a detailed explanation. Let me conclude the talk. I presented a method for finding a limit cycle solution of an uncertain Lurye system. The method is constructive and provides the required worst-case uncertainty sample, initial conditions, and the exact nonlinearity with minimal slope. In the future, we plan to generalize this approach by extending it to more complex uncertainty structures. If you're interested in this solution or have any questions, please don't hesitate to contact me. Thank you for watching, and I hope to see you in future conferences.